coming to the training. So today we are having the training course on fundamentals of electrical machines, stroke electrical generators, stroke electrical motors. Broadly, we are going to learn about generators, motor, the fundamental, the theory, and then we are going to see how this is connected to real life application. Yeah. So before we start, we do some ice-breaking session, okay, just to get to know each other, our expectations, our background. So my name, I'm going to enlarge this one. So my name, I'm Jiashen. My surname is Tay. Graduated from University of Manchester with my PhD in electrical engineering. So after I graduate, I work in USM since 2016 until now. So it has been about 8 years in USM. So my work in USM, so this is my USM profile. So in USM, my work is mainly surrounding lecturing. Lecturing is one of our tasks. Aside lecturing, we also perform research, right? That's another major branch of our work. So in my research work, I work on power grid study most of the time, yeah. And in the power grid studies, we can branch into power system assets, power system reliability, power system dynamics, what else? Protection system device, and then also nowadays the more modern type, the cyber physical connections, the SCADA system. In my work, I focus mainly on power system reliability, so not so much on the dynamic side. So I focus on the steady state analysis most of the time. So that's a bit about myself. I would like to invite the participants, right, to maybe introduce yourself. So I would like to invite Mr. Chan, right? Mr.
Yeah.
Chan from Sarawak Energy.
Yes.
Okay, maybe introduce yourself a little bit. Yeah.
Okay. My name is Sarawak Energy. My name is Chan, so from Sarawak Energy. So our company actually is a similar function with TMB, where we generate power and then sell, distribute to the public, similar function to TMB. I graduate. Actually, I'm study my profession is half technical and half management. So because my technical is only until diploma, and from Australia Vocational School, and then my degree actually is technology management. Okay. So basically now I'm with remote monitoring diagnostics center in SCB, where we actually monitor the asset performance for the power generation asset. So I'm in electrical section, so I'm in charge of monitoring the electrical equipment's health and performance. Our center is really just formed in 2022, where we first operate, and currently we only have one station that connect to our center, so that we can monitor online, which is a digital twins for our generations. And then currently we are doing our second station, which is a GT CCGT generations in Junu. The first
CCGT.
Yeah, the first station that connect to our center actually is a CFB boiler. I think it's the biggest CFB boiler in Southeast Asia.
Okay.
The biggest CFB, which is the single set is 312 megawatt per set. So the second power station that coming to our center is Tidong Power Station, which is a bigger power station with single block of 412 megawatt. We have a few blocks on that. So we're going to connect this one hopefully by end of next year. So that is CCGT set. And we are expanding the whole project take I think 10 years to complete, because we have so many plants across Sarawak that we're going to monitor, start to monitor online. Then the other piece by piece system that we can monitor in our AMET center is the transformer ODGA, online digital gas analysis.
Yes.
The stations, motor, OBMS, the online vibration management system. These are the things that we can monitor at our station.
Yeah.
Even remotely, like now I'm here, I also can monitor
Can
our
monitor.
system here.
So how long have you been with Sarawak Energy?
I've been with Sarawak Energy for more than 25 years.
More than 25.
Yeah. So with 12 years in operation, 5 years in maintenance, and then the rest of the year is in this operation excellence division.
The
Yeah.
new one, the
The
monitoring,
new, yeah,
the remote
yeah,
monitoring
yeah,
systems.
yeah.
I see.
Yeah.
Also, you guys also monitor the performance of the transformer.
Yes.
So you have the sensors there send data online, real time.
Yes, the data that we get from the transformer are actually the dissolved gas signal and also the pressure, the temperature
Yeah.
of the transformer through this
The gases as well.
the gases,
Yeah.
the gases. Then from the gases that we have a software that to analyze using the IEC gas ratio, double triangle,
Yeah,
this kind
yeah.
of analysis tools to analyze the condition of the transformer.
So
This
gas
is-
analysis.
Yeah.
All right. Okay. So hopefully the training today focusing on electric generators is going to be beneficial.
Pro One Design Engineering.
Pro One Design Engineering.
Yeah.
Okay.
My name is Sharina.
Sharina.
Okay, our company is a supplier for car company such as Proton, Honda.
Yeah. Okay. So you supply, I guess, something related to the cost as well,
Yes.
generator and motors.
Yeah.
Okay. So roughly how many years have you worked in the company?
About 6 years.
About 6 years. I see. So I guess you are interested to learn the fundamentals of
Yeah,
motors so that
I'm
you can.
here for training for fundamental electrical machine.
Machine.
Yeah.
I see. To maybe relate what you are doing with the theory and the science to back up the
Yeah.
practical, I guess.
Yeah.
Okay. All right. Motors or the DC machine, right? All of them are governed by the same set of machinery principles. So if you understand these machinery principles, then we can extend our applications, right? Rather than we dive into, okay, if you want to know about synchronous generator, then we dive into synchronous generator, but then the concept behind, if we don't understand, right, then the flexibility of the application will not be so robust. Okay. Just a quick, so I think everyone knows this, yeah. So electrical machine converts mechanical, electrical power, so I think it's not I don't go deep into it. But the main thing I want to stress is the magnetic field. So magnetic field is something I guess most people are not so familiar with because we don't normally able to visualize how magnetic field is. But then this will be the main thing that we are going to study here. We're going to examine here because the magnetic field interaction of the stator and the rotor are the one that causes voltage to be induced. Okay, these are many of the terms that we're gonna listen to, and then that is how generators produce power. And for generator to function as a motor, that will be only the opposite of it. So by manipulating the magnetic field, we are able to convert generator to motor, motor to generators. So let me shift this a little bit. Okay, so the main parts about this electrical fundamental is later. There will be some simple calculations, yeah, that we try to take this fundamental, put inside a simple machine and see how those fundamental components interact in a more complicated generator and motor later, maybe for the next several days. Yeah. Transformer. So just now, before the video start, I had a quick chat with Chris. Chris said he's also interested in knowing transformer. So, correctly, because generators, motors, and also transformer, right? They are interrelated. Okay, so as we know, transformer they convert voltages between one level to another. So as generator and motor. Okay, although generator and motor we don't convert voltage level, but the principle behind is the same. It's based on magnetic field induction. So in transformer, the voltage transfer between high and low through magnetic action. Generator and motor also same. Okay, through magnetic action, and then we produce motion in motor, or we produce power in generator. Yeah. Okay. Nothing for this. Okay. So one thing to set up in this training module or training course is that when we describe generators and motor, right, we always assume that the rotation counterclockwise, right, counterclockwise in this direction. We assume that counterclockwise is the default and the normal condition without mention. Yeah, that's the default. The clockwise one would be the abnormal part, right, the non-normal conditions. Yeah. Okay, I want to go into this. Yeah. So first of all, angular position. So angular position is everything is relative. Yeah? Relative. We measure in relative between rotor and stator. So angular position normally we measure in terms of radians. Okay, degree yes, but not so much. We normally measure in radians. Later we'll see. Yeah. So motor and generators, they are functioning in circle, right? So everything we measure in revolutions, we measure in angle. So the analogy to angular position will be like distance in straight line. So in straight line we measure distance. In rotational motion we measure angular position. So that's one thing we need to know, angular position. Yeah. Angular velocity. So I think this one is how to say, the word velocity also connect that naturally, right, to the velocity we measure in straight distance. So velocity we normally measure meter per second, kilometer per second, right? That's for straight line velocity. But for angular velocity, then it will be some sort of a distance divided by time, right? So angular velocity in the angular motion, because in the angular motion we don't measure a straight line distance, we measure in a circular distance. The circular distance is called the angular position that we see just now, delta over t. Alright, so don't mind the differentiation equation here yet. The differentiations only shows the difference here. So the difference of delta shows that the difference between two distances, right? If you want to measure velocity, you take distance A minus distance B divided by the time in between. Yeah. So same as angular velocity. So that's it. One thing to point out, because we are now talking about angular velocity, we got rotation, right? Rotation, and then we got one thing that comes into mind, the frequency of rotation, right? So the frequency of rotation is given to us by the angular velocity is given to us by 2 pi f, right? So that is the calculation part. Yeah. So we take 2 pi as a constant. Okay, 2 pi multiplied with the frequency in hertz will give us the angular velocity in radians. So later we'll see some calculations to apply all these things. Yeah. So we got, let me write it down here. Let's see. So we got angular position, the first thing, and then we got angular velocity. So angular velocity is related to this one, given to us by delta. Delta means the difference. Yeah, the difference. It's only difference of the theta over t. Can see, yeah, Chris? Okay. Then you got angular acceleration. So same thing, same as your vertical acceleration. Acceleration is change of velocity, the rate of change of velocity. Same here in the angular motion, you got angular velocity. So it will be the change of your angular velocity over time. That will give us angular acceleration. Yeah. And then the torque. Okay, torque. So in straight distance, we talk about force. Force, right? Force. We all can visualize force. The more force we have, the faster a certain thing can start moving. So in angular motion, we don't call it force, we call it torque. So we often hear now with electric vehicles, yeah, we talk about what is the horsepower, what is the torque. Okay, what is the Newton meter of the car, the torque, right? So the torque is the one that gives us the acceleration, the feeling of pulling back. Yeah, that's torque. So you can imagine torque as something like a twisting force. Yeah, twisting force. So the words here is as a personal notes. Okay, when in your own time, if you want to go through, you want to revise at least for more descriptions of the torque. But for now, we can quickly imagine torque as something like a twisting force. So the four components that we need to describe functions of generator and motors will be torque. So something like a twisting force. Yeah. Okay, now, so imagine this one. Yeah. Imagine that you have a rotor. Okay. So we have a stator, the body of the generators of the motor, and then inside you got rotor, right? The rotor. So this will be the rotor. Okay. So we calculate torque. Okay. In a straight line distance, we calculate force as mass multiplied with the acceleration. Right? But then torque, right? In an angular position, we need to see where we apply the torque. Yeah. So for a rotor like this, okay, if you apply the force or the torque, yeah, central to the center of the rotor, then of course the whole thing will not turn. Logically, if you want to turn this, we need to apply somewhere here or somewhere there, okay, along the side, so that we can start turning the rotor. Yeah. So we apply it somewhere here. Okay, we apply a force here. So the torque then can be calculated as the distance between this and multiply with the force. Okay, so distance here multiply here. Okay, that will give us the torque. Okay, so don't be confused force and torque. Yeah, so torque you need force and distance. Okay, the distance between the central to the line of force. Okay, this is what we call the moment. Okay, the moment of force. So you multiply these two things, you get torque. So it meaning that if we are unable to apply a big force, but we want a big torque, we can increase the distance here. The larger the distance, meaning that the further away from the center of the rotor, the bigger the torque it is for the same amount of force. Applying here and applying here. Yeah. So what is all this trigonometry over here? Okay. So don't mind the trigonometry for now, but let me describe in a very simple way how do we apply this trigonometry. Two things only, right? Two things only that we need for trigonometry in this training module. Cos and sine. Okay, so let's imagine the central here. Okay, and then this is the line of force. And the line of force. Okay, and then the radius. Okay, the radius. This is the actual distance, yeah, the actual radius, the physical distance, the physical radius of your circle, right? So this one is an actual measurements in terms of centimeter, meter, millimeter. Okay. So the theory, yeah, the theory says that for calculation of torque, we need to take the radius, okay, multiply with the force. The force is vertical like this, and then the radius is at a slanted angle, okay, like this. We cannot take these two multiplication. Okay, what we want is that when we say the multiplication of radius and force, yeah, what we want is the perpendicular component of those two things. Meaning that I want to find the equivalent of this force here. Okay, the equivalent of the radius here. Yeah. So this is the actual radius, but it's not useful for our calculations. What we want is this component, multiply this component, that will give us the torque. Yeah. So this component, okay, this horizontal component, we need to convert this to here. To convert this to here, then we need to apply trigonometry. So a simple way, right, that I always say is, yeah. So this angle we definitely know, okay, because this is a vertical angle. Okay, so the angle of this radius from the vertical position down here, we definitely will know this angle, theta. So this theta is what we see earlier, the angular position, right? So your rotor, okay, this is the center of the rotor, has rotated a certain distance, all right? The rotations of this distance is described by this angular position, theta. So we know this theta. We want to find the equivalent horizontal distance. We take this, multiply with the sine of theta. So why do I know sine? The simple rule of thumb is this. If what you want to find, yeah, if what you want to find is not next to the angle, what I mean by next, this one is next to the angle. Okay, or you can imagine that your angle is stick to your line. You can imagine this way, yeah. So if the angle is here, then this will be cos theta. So in this case, the angle is here. This is cos theta. Okay. So when to apply cos or sine? To apply cos and sine, you look at the angle, the theta. Where do we draw it? If you are drawing between this blue line and the black line, the one that is connected to the theta, we write cos. The one that is not connected, we write sine. Okay, that is the rule of thumb, so that we don't have to always think when we want to do the calculation, right? Analyze. But later, yeah. So with this, if we know what is the r sine theta value, because we have the theta, the angular position, okay, which we can measure. The r is a constant, which is the radius of the rotor. So both we know, we can determine what is the horizontal component of this radius, multiply with the force, then we get the torque or the twisting force. Okay. So how do we actually get these? Yeah. So if I can quickly explain the mathematics behind the rationale behind r cos and r sine. Yeah? If I take this, I draw it out. Yeah? If I take this, I draw it out. Okay. So this is the theta. Okay. So this x and this y. Yeah. So this r cos and r sine theta, okay, derive from the fact that cos theta equivalent to the next one divided by the hypotenuse, right? X over r. Okay. and then the sine theta equivalent to the opposite divided by the hypotenuse. Yeah. Okay. So from here, if you want to know y, then you just take the r over. So that's how we get the r sine theta and r cos theta. Okay, but of course we don't want to go through this all the time. It's hard to imagine. So the easiest way is remember, if the angle is not stick to the line that you want to find or the component that you want to find, then you apply the sine. Okay, if the theta is fixed or stick to the component that you want to find, then you apply the cos theta. Okay, so r cos for the one that is next to it, r sine for the component that is not next to the angle. So that's how I remember it. Okay, so this will be utilized in all the later part of the analysis. Yeah, so quite important. Okay, so we got the top, and then okay, so this is another way to describe the top. This is rarely used, so we skip this. And then work. Okay, work. Something just to put it out there. Not so much we deal with work, but we may require it. So work is mathematically is the integrations of force. So what does integration mean? Integration in simple terms is just the summation. Okay, it's just the adding up of all the components that you have. Why they use integration and not summation, right? Why they want to make it so complicated? Because integration can better describe the small changes of force. Alright, small little changes. When small little changes, right, if you don't apply the integration in terms of mathematics, we cannot capture those incremental changes. So to capture incremental changes, when add up, they are quite significant. Yeah. So that's why they apply integration. Okay, that is the reason behind. But the practical implication is summation. Simple as that, summation. So so work, right? Can I rub this? Yeah, rub it. Yeah. So work, right? So for work, we need force and then we need distance. Alright. So we already got a twisting force that we have defined earlier, which is our radius multiplied force. Okay, I would use a cross behind. This is to indicate perpendicular. Yeah. I want the component that is perpendicular to the force. I want the multiplication of that. See the force multiply the distance. Force and distance, you get work. Same as in your straight line component, straight line analogy. Yeah. If I have huge force, I'm exerting a lot of force, but I'm not moving in distance, I've not done any work. Right? Same here. So here you want to apply a big force to the angular motion, and then you multiply with the distance theta, then you get work here. Okay, the torque multiply with your distance. Okay, we don't call force in angular motion because in angular motion we call it torque, a twisting force. Yeah. So far we got 5 components. Circuit that we know, we got voltage source, and then we got the particular resistance, then got the current. So this one is quite simple. Yeah, V equals IR. But then in a magnetic field circuit, we have the equivalent as well. Okay, instead of voltage source, we are talking about with this weird symbol. This is the Greek letter F. We call it MMF. The direction of the palm represents the directions of the flux flow. Yeah. So that is the analogy. Okay, that enable the drawing of this chord, right, where we draw the direction of the flux. Okay. So the direction of the flux is something that we need to go through as well in generator and motor. It will be very confusing. In generator and motor, we have a lot of poles. Yeah, you got a lot of poles. And then when we look at the poles, yeah, then you have certain poles that current entering, current exiting the poles. If we are looking at the poles from the front, so the direction of the current flow is we can determine using this one. Okay, fundamentally we can determine this one, but in practical, how do we do that? That we will come to it when we come to that section. Yeah. So, as I mentioned, yeah, this is just a repetition of what I mentioned. Ni will give you the voltage, okay, or the MMF, which is this, okay. And this is basically the Ampere's law, which is given to you by this one. So this is a summary of this one, yeah. Okay. Now, one thing I left out just now for the calculation of flux over here. Yeah? Flux. For current, okay, for current, we measure the current. Okay, we can measure the current. We have ammeter. For magnetic field flux, then how do we calculate that? Okay, we can calculate it with this relationship over here. Flux equals to B multiplied A. So what is B over here? The B is the magnetic field. Okay, we have a magnetic field that's flowing. Okay, the magnetic field, imagine, is something like a water. Yeah. So the water flowing through a particular area. Simple calculation, shall we? Yeah, we go through a simple calculation over here. Okay, now you have this transformer core. Okay, transformer core. So in the generator and motor, we will have this because generator and motor didn't have a core like this. But then the exercise here, yeah, the exercise here is used, I would say, is used to describe the concept just now. Okay, so something to take note: the width over here and the width over here are different. Yeah, this is 10 cm, this is 15 cm, so it's different. Okay, and the idea here is to calculate what is the flux, okay, and also what is the MMF, and also what is the total reluctance. So that is the idea here. So that we're going to construct this circuit. Okay, we know that this one can be represented with this, with MMF, with flux, with reluctance. Okay, you want to convert this complicated diagram into something simpler like this. Okay, so how do we do this? Yeah. So the first thing, flux is given to us as these equations over here. Okay, and so reluctance is given to us by this equation. This is basically just the length over the a constant for the material multiplied with the cross-sectional area. So what is this? The length will be this. Yeah, the length will be this. Okay, this is the length. Okay, so there are two types of length over here, if you notice. First of all, the length from here to here will go through a certain cross-sectional area. Okay, if you can notice here, the cross-sectional area over here is, you can take it, okay, is this, which is this, yeah, this multiplied with the depth of it, yeah. So this is 10 cm. The depth is 10 cm. Okay. But when it comes to here, this is 15 cm. The depth is 15 cm. So the cross-sectional area here and the cross-sectional area here is different. Yeah. How about here? Here is 15 cm and the depth is also 15 cm. Here also 15 cm and the depth 15 cm. So it means what? it means that the cross-sectional area here, here, and here, same. But the cross-sectional area here, different, smaller. Okay, this one is 10, 10. This one is 15, 15. So it means that we got two types of resistance or stroke reluctance. Yeah. So first thing that we can calculate is this now, the reluctance. The length, the first length and the second length. Okay, the first length and the second length. So the cross-sectional area of the first one and the second one. So if you notice here, the first cross-sectional area is 0.01 meters squared. So how do we get this? Simply take 10 multiply 10. 10 multiply 10, you get 100 cm square. Right? 100 cm square, you want to convert to a meter square, you divide by 1 meter to use 100 cm. So square will be 10,000. Yeah, 40, 10,000. Divide by 10,000. So 100 divided by 10,000, you get 0.01. Yeah, right? 1, 2, 3, 4. Yeah, correct. So divide by 10,000. Yeah, that's how you get the number here. The same here, 15 cm, 15, no, 150 cm square convert to meter square, we divide by 10,000. Okay, so the first area and the second area. The first area here and the second area here. Okay. And this one is how to say, the permeability of the conductor will be the same throughout, so both will be the same. And you got the length 1 and the length 2. Alright? So you just apply this, then you get the reluctance 1 and 2. So we've solved the first step. R1 and R2, we got it. Yeah. If you want to simplify this further, you can sum both of them up because they're in series. Okay. The MMF will be direct. Okay. The MMF will be the number of turns multiplied with the current, then you get NI. Okay. Which is number of turns is 200 multiplied with 1 ampere, you get MMF. And then if you want to calculate the flux, then it will be the same as your circuit. Yeah. So if you have V equals IR, here we got MMF equals to flux R. Okay. So in your normal circuit, V equals IR. In a magnetic field circuit, you got flux equals to flux R. So the MMF equal to flux R. So that's how you get this. Okay. Over here. Yeah. MMF equals to flux multiplied R. Okay. So you just take over the other side equation, simple calculations, then you get flux. So flux, we normally measure in Weber. Okay, this is something I want to bring home. Okay, measure in Weber. Okay. Okay, something that's interesting relationship which governs also our generator profile. Okay. One interesting is that when we plot the chart of flux and also the number of turns, okay, from this calculations, we think that, okay, if we increase the number of turns, if I increase the number of turns, yeah, the number of n, okay, if I can put it up in the equation, the MMF equals to flux R. The MMF is Ni. Okay, by right, if I increase the number of turns, number of n here, so in a generator it will be the same. If I increase the number of turns around my poles, my windings, I increase the number of windings there, MMF should increase, right? And then as MMF increase, then the flux should increase. but not in magnetic field. There are some exceptions over here. So when we plot the relationship of flux and the turns, okay, you see later there. The relationship is like this. So initially, yes, I have a huge increase in my flux, but then after a while, it sort of flattens out. Okay, why is that the case? This has to do with magnetic saturation. So in your conventional circuit, okay, you have to always bear in mind, in a conventional circuit, we are dealing with current, and in the magnetic field, we are dealing with magnetic field. It's not current, yeah? The concept is similar, the calculation is similar, but one is current, one is magnetic field. Remember, magnetic field to flow, right? You need a medium. That medium is the magnetic core. So magnetic core, right, when magnetic field start to flow, okay, initially the magnetic core is empty. There's no magnetic field inside the magnetic core. But as magnetic field start to flow, the magnetic core will accumulate the magnetic field. So the core will start to accumulate. After a while, the accumulation saturate. When the accumulation saturate, the core cannot accept more field than that. So that is what happened here. The magnetic field start to accumulate in the core, and then as the core become more and more saturated, then the accumulation become slower and slower and eventually flattens out. Okay, so similar like we are filling up a bottle. Okay, initially we can fill up the bottle fast, but after coming up to the top, then we slow down, right? Same thing there. So when we plot the flux and the number of turns, right? Based on the calculation, yes, theoretically the turn increase and then the flux should increase, provided I have an unlimited, okay, permeability, unlimited, a super magnetic core, but we don't have that. So if I can plot this against this, okay, and I know that this is related to like to the flow, okay, of the flux and the area, then I can also relate the V, which is the flow, okay, the flow of the flux with something similar to this, with the magnetic field as well. Okay, this H is given to me by my current I. So same thing. Alright. So in generator, we talk about knee point. So in generator or even in motor, we are always operating in this region, the saturated region, right? It makes more sense. Why? Because we will get the most torque out of it, the most voltage induced out of it. Okay? And why would we want to operate in this region? We will not want, because here we are not fully utilizing our magnetic field material. Okay, so in your generators and in your motor, right, the operation is exactly the same as a transformer. Okay, the only difference is that in transformer is not moving, but generator and transformer, generator and motors, right, they are moving. Okay, you have a moving part there, but the actions are all the theory behind, right, are all the same. It's based on transformer action. That's why we say that your generator and your motor is your moving transformer. Okay, it's transformer action, and you got this relationship. Yeah. Okay, so this is X loss. Yeah. So maybe can I ask a little bit? Do you deal with hysteresis loss in your operation of generators?
What is hysteresis loss animation?
Hysteresis loss in the heating of the core.
Yes.
I think normally.
But we did not count. Because we know that the generator will have heat loss, but we don't know how to measure and then how to calculate yet.
I see.
Yeah. Because just now when we talk about the magnetic field, magnetic flux, it only deviate or changes due to the current itself or the voltage. With the voltage, let's say now our motor now rated at 6.3 kV, with a rated current, let's say 20 amp. If the voltage drop, the operating voltage, let's say now it's become from 6.3 to 6,000 or even lower 5.7. So the current relatively will be higher in order for us to get the operating power for the motor, right? So
Yes.
this one, but this one will affect on the magnetic flux of the motor. Will it be lesser or stronger? Because the current now is higher.
Increase in the years.
Yeah.
It will. The flux will increase. You'll get higher flux out of it.
So in this scenario, the motor is actually more efficient or less efficient?
Okay. More or less. Okay, more efficient or less efficient. It depends on the curve here. Alright? So, if you are already operating in this saturation region, by increasing more current, you won't have much effect on how fast your motor can turn or how fast your generator can turn. I would say electric machine in general, or how fast the electric machine can turn. Okay.
For electric machine, and then because it's a synchronous speed, it cannot be turning faster than
It cannot.
3000 RPM.
Yeah.
So that speed is already fixed, but the current increases. It will not, even though the flux is increasing, but I think because of this, the power factor of the motor, let's say rated original is 0.85 for the motor for the power factor.
Yeah.
So now the power factor maybe it will be affected, or the angle will be affected by this voltage loss. Because the motor actually maybe consume more mass than it's supposed to be.
Yes.
So this one, the efficiency actually will improve, right? Or let's say because of heat.
Yeah, no direct answer to that. Yes, what you ask is actually is an interesting question. In the synchronous generator part later,
Okay.
there are scenarios that we will see. Unity power factor, how does it look like? Leading power factor, lagging power factor, how does it look like? So 3 different power factor scenarios, like you mentioned. Yeah, it will affect the speed of the rotation, the efficiency of the machine. Yeah, so we'll see that. But as you mentioned here, now the question you mentioned, yeah, just to share, the complexity is there. The complexity is not direct because there are a lot of factors together. For example, in this case, yeah, even with only 2 components, flux and current, then we are talking about whether you are in a saturation or non-saturation region. So it's not a straightforward answer that, okay, if I increase my current, will my flux increase? And then again, you have to talk about synchronous generator. You have synchronous speed, okay? And in fact, right, to sidetrack a little bit, for synchronous generator, the speed of rotation has nothing to do with your current. It has to do with the field, rotation of the field, magnetic field. So, we will go through that. Yeah, go through the synchronous generator. So, but just now I asked the question whether you deal with hysteresis loss. Yeah. Yes, you don't calculate it. Why? Because hysteresis, in actual, it will manifest as heat. Yeah. So where the heat comes from? Yeah, the heat comes from this curve relationship. So without going into the words, the description of the words, I would like to explain using a diagram will be clearer. Okay. So you got this diagram of your flux versus your intensity. Okay. You got your flux, and then the relationship will be, if you are talking about flux, okay, with the symbol like this, flux versus your MMF, or you can describe it using the intensity of the flux. Intensity of the flux is basically this multiplied with the area, okay, with H, the intensity due to the current, okay. Normally we use this, the flux and the MMF. Okay. So if you increase the MMF, meaning that I increase my current. Okay, start from A point here. So in your electric machine, yeah, if I apply current onto my stator, okay, I apply my current onto the stator, your stator is basically an electromagnet. It's not a permanent magnet, it's an electromagnet, meaning that the the magnetic field will come only when there is current. Okay. So I increase my current, meaning that I increase my MMF. So you will increase the flux flow in the stator core. Okay. It will go up. Okay, it will go up and then saturate. It will saturate. So at one point, the further more current you apply, it doesn't increase the flux anymore. So you waste money. You just pump in more current, but you don't get more out of it. So it comes to here. What happened when we shut down, right? When we switch off the current. When we switch off the current, yeah, you don't go back the same path. It go the other path. Okay, from here, it goes the other path. It come back here. Original path is here, but then it comes back here. Okay, that's this is the behavior of the core, yeah, or the behavior of the magnetic field. Later we relate this to our real life application. Come back here, and then this is when we start to reduce the current, not just shut off completely. Okay, we reduce the current. Logically, we think that reduce current come back here, but no, it's actually come back here. And then we reduce further, we come back here. We follow the different path. Okay, so when we are here, okay, so now I switch on my motor. Come here. I reduce my current, I switch off. We think that we are here, but actually the magnetic field of the core is actually here. So first stage, I switch on and off. Then second stage, I want to switch back on. When I want to switch back on, yeah, it goes from here, not from here anymore. It goes from here up. Okay, and the process repeat. So you can think of it like this. You start the motor or you start the generator fresh. And then after operation, it will be like this always. So it formed this nice figure over here, okay, with an area over here. So this area, yeah, if we calculate the area over here, this is what we call the heat loss due to hysteresis. Okay, hysteresis, meaning that the current, there's always a residual current in the core. How is that so? Yeah, it's actually given to us by this diagram. So think of this core, yeah. Think of this core that you can split into all these compartments. Okay, and in all these compartments, you got your little magnetic arrow. Okay, so they are all random initially. Okay, so when your magnetic core is random initially, okay, then there is no how to say magnetic property lah. So the magnet cannot have no north-south. Okay, but when we start to apply current, let's say from this direction to the next, yeah, when we apply the current from here to there, then the magnetic field will align itself into the direction of the current, but not perfect. Alright, it will be mostly in that direction, but not perfect. Okay, something like this. Yeah. So when I remove the current, do they go back to the original? No, they don't. Right? Because these are random to start with, to begin with. So when I apply the current, force it in one direction, and then I remove it, the little magnetic field inside will not go back to the original position. That explains, okay, this explains why we have the hysteresis loop. This is what I call the hysteresis loop. This explains why we have this behavior. Okay, if in the ideal situation, what we apply, okay, what we apply can go back to original. Okay, after we remove the current, then we will not have this loop. It will be a straight line always all the time. Okay, that will be the ideal case, but that is not. Okay, in fact, we have this. So because of this hysteresis loop, you often heard that our stator core are made of laminations of metals. Okay, the lamination want to be as tight as possible. The lamination want to be as thin as possible. Each lamination. Why? If the lamination is thin, then less current can flow, or less field can flow. Right? So the behavior of magnetic field field, fortunately, okay, somewhat similar to current. So if current cannot flow, magnetic field also most likely cannot flow. So if we make the plate thin, less area for the field to flow. But thin got problem. Thin meaning that we can accommodate less field. So how do we solve that? We take a lot of those small plate, thin plate, jam pack them together. Okay. So that is the reason behind it.
Is it similar to iron loss, this one?
Iron loss, no. Iron loss is iron loss is due to current flow. I squared R. Iron loss is I squared R. This one is hysteresis. This one is due to magnetic. It's something like a I squared R for magnetic field. Yeah, I squared R for magnetic field. Yeah.
This one, how, because I think the generator, the motor, during the design, they already calculated and then come up with this laminated core to prevent these losses. So if this one is already fixed, how can we control to minimize this, let's say like during the operation from time to time, how are we going to reduce these losses to a minimum?
The hysteresis one.
Yeah.
To reduce it to minimum is down to the the material of it. So let's say from time to time, yeah, what you do is that you don't drastically on and off. Okay, like normally generator we say that okay, when we switch on, we don't normally switch off if we don't need. Okay, you don't like when you like it, then you switch on. When you don't like it, you switch off. It's not like that, right? Because why? When we operate, yeah, when we switch on, let's say I stay here. Okay, I stay here, then the plug will stay here. Alright? If I on off, then it will be like this. And like this, then you got heat. So that's one thing. Operation. Nothing much we can change in the operation part. To avoid this. Because this, even to avoid this, it's come down to the manufacturing part. The lamination have to be as tight as possible. So in operation, maybe we can examine, okay, is there any gap that is bigger? Not to say gap big to the extent we can see, but big relative to the original. Yeah, so why we jam pack the lamination is so that the air gap is as little as possible. Okay, little air gap. Air gap, right, has to do with the calculation just now that we didn't go through for the transformer one, because the air gap, okay, this one, yeah, this one we calculate the reluctance, yeah, L over mu A, okay. Just now the mu here is the permeability of the material, okay, but actually this one can be broken down, okay, into the material, the mu of the material, I would say M, and the mu of the relative. Okay, so this relative is to describe the relative strength of your material with the air. So if I have more gap, this one increase. Okay, so this one increase, this one reduce. This one reduce, flux increase. Flux increase, more heat. Yeah, that's why we want to have as little air gap as possible.
This one, let's say, generator is not designed to frequently start-stop. Let's say we frequently start-stop our generator. So what will happen? The first thing that we can tell the station, hey, this is not the correct practice to do so. By doing so, actually you shorten the lifespan. What are the variables that can cause the lifespan of generator to be shorter lifespan? Is it because of the heat that will present in the generator of frequent start-stop, because of the losses become more along time? You frequently start-stop, then this one maybe become bigger. Is it the size, the S become bigger?
The area?
The area become bigger.
Yeah.
then the losses will, in terms of heat, become more, maybe you start for more than 20 times. Let's say the first time and the 20 times, the heat generated inside the generator become more. So like that, can we say it with that one?
Yeah, over a long time. Over a long time, like maybe you talk about 10 years of this kind of
Or we
practice.
can say the degradation of the insulation
Degradation. Yeah.
later.
Yeah. This one is just still surface lah. Like we go through the next module is a synchronous generator. Then we see more details. Okay. But hysteresis law. Normally hysteresis law, just to put it out there, explain it, because later on we see power. We have a power diagram to see along the way from input to output. Okay, what are the losses? One of these is hysteresis loss. So I just want to explain here. Is how does this hysteresis loss come from? Okay, and then this is hysteresis loss. So what about eddy current? Eddy current is just leakage. Okay, leakage of current flowing in the field all the time. Leakage. That's eddy current. Okay, core losses is not you mentioned. All right, so we are about to go into. All right, about to go into the four fundamental movement just now. Okay, the rings is onto your rotor. Okay, so this brush and the slip ring, right? They will not rotate together with your rotor. So as the rotor rotates, the slip ring and the brush will stay there. Okay, so that is just a way, right? Just a way for us to connect our DC power onto our rotor. That's it, right? So in simple form, just think of it as a way for us to connect DC power to our rotor to produce magnetic field for the rotor. Okay, right? That we draw for us to understand how does the stator and the rotor interact with each other. So you got here the exciter. This is what we call it, exciter. That is connected to the rotor, the DC source. Okay, the DC source. And this DC source, okay, we apply a DC source, okay, as we see earlier this morning. A flow of current produce magnetic field. That is why it's called exciter. We use this magnetic field to produce magnetic field, to excite magnetic field or excite, to induce voltage at the stator part. So that's why it is called exciter. Right? It's something to start the movement. So we have here the exciter and the rotor. So if you notice here, in terms of electrical circuit, the exciter circuit here and the stator circuit here, right? They are not connected physically. Okay, this dashed line is an imaginary line that we draw ourselves. Yeah, and they shows that the rotor and the exciter, the rotor and the stator, yeah, they are not connected with each other. Okay, so but then they are connected magnetically by using transformer action. Okay, the rotor here will transform or transfer the magnetic field from the rotor to the stator. Okay, that's why we use this inductor, okay, to show the magnetic coupling. So due to the magnetic coupling, this will produce current flow, okay, magnetic field induced in this stator winding, and then current flow. So don't mind about this. If you see this, this one, these are just this arrow, okay, arrow with the black. These are just to convert AC to DC. Okay, they are just, think of it like a switch. Okay, like a switch. Okay. All right. So when we talk about synchronous generator, yeah, we talk about synchronous speed. So synchronous speed is something that we have known already from our AC machinery fundamentals. Okay, the electrical frequency that is produced by this synchronous generator, they are related to the mechanical speed, of course, okay, of your rotor and also the poles, the number of poles, yeah, in my generator. So these are the two variables that we can play around to achieve the desired electrical frequencies that we want. So you can either increase the speed of the rotations or increase the number of the magnetic poles. So we need to strike a balance here. Yeah. It's easier, okay, it's easier to increase the number of magnetic poles than to increase the speed of rotation. Because for magnetic poles, right, we just increase the number of windings. But for mechanical speed, we need to spend a lot of resources. We need to burn coal, we need to boil water, okay, to boil the water to produce steam. So you can have various ways to produce steam. You can use coal, you can use gas, you can use nuclear, you can use renewable energy, okay? Different ways, yeah, to produce these movement. So in Sarawak Energy, what resources that you use to produce the prime, to produce the movement of the rotor?
We have turning gear. Turning gear is to please turn the rotor to a bearing speed of 4 RPM per minute, and then excite the first magnetic field come from battery.
Oh, from battery. Yeah, exciter use battery only. How the prime mover?
Prime mover.
What resources you use?
Turning gear motor. We use the motor turning gear to give the rotor that couple with a bearing speed of 4 RPM.
To start the first movement.
Yeah.
I see. And just now you said Sarawak Energy, you got your own Sarawak Energy resources.
Yes.
What resources that you guys? Coal. That's right, coal as well. Gas, no, I think.
Coal, no, only coal. Only coal.
Okay. Gas is expensive. Coal is cheaper and more common in Malaysia. Yeah. Okay. Just to give example, yeah. Look at this simple calculation over here. To generate 60 Hz of power in a two-pole machine, right? So if I want to achieve 60 Hz here, and I only have 2 poles, the calculation would be given to us as a simple calculation. Yeah. Right. So if I have this is the equation. So if I want to achieve 60 Hz, and I fix with only 2 poles, yeah, which is a non-practical configuration, yeah. The Nm, the mechanical speed, will work out to 3,600 revolution per minute. Okay, 3,600 revolution per minute is very fast. That is not healthy for the mechanical configurations of the rotor, because it will, when the rotor turns too fast, the center of axis will be thrown out of the position, and that will cause bearing vibration first, and then the bearing and all will be dislocated. So instead of having 2 poles, yeah, we can increase the number of poles so that we can reduce the revolutions, okay, the revolutions of the rotor. So that is what we can play around. Okay, so far we are still on the surface, yeah, on the surface of the operation. We haven't go into the magnetic field and the electrical operation yet. All right. This is what we have earlier. Okay. This is what we had earlier. Okay, to induce your MMF, which is your induced voltage lah. We know that it is number of turns, okay, multiplied with the flux and then the frequency. The frequency here refers to the frequencies of your electricity, okay, 60 Hz, 50 Hz, and so on. So if you examine this equation here, there are several constants here. These 3 terms are constant. Okay, so I can ignore this, okay, to call it a constant K. So this constant K is typically provided to us by the manufacturer. Okay, it's a constant that stays with the generator forever, because that is the number of turns and then multiply with two constant. Okay, so K is a constant. What we need to concern is only the flux and also the omega, which is the revolution, okay, frequency, the turning frequency. So this one is just expressing your K. Okay, there are two ways to determine your K, but this is the how to say, the manufacturing constant. Okay, so this is just to put it there so that for information. All right. So the same behavior that we have seen in our AC machinery fundamental also applies here in our generator. Okay, which is to say is that your flux versus your field current. Okay, so remember your field current is at your rotor. Okay, and we are talking about the rotor. Okay, and then you've got your stator. Okay. And draw it in 3D. Okay. So the flux here, as we apply the field current, okay, onto our rotor, yeah, we don't expect the flux to keep on climbing. Okay, the flux will saturate. So this is what we know from the AC machinery fundamentals. Okay. So if I can say that the flux is constant, therefore the induced E will be constant as well as my field current approaches a certain values. Okay. This is because we have earlier on we have this equation, isn't it? Okay. So if I have a relationship for my flux, okay, then my EA, since my EA is in the direct proportional with my flux, therefore my EA behaves in the same way as my flux. Okay, so far so good, yeah. All right. So there are one terms over here that we need to differentiate. Okay. This voltage EA, right, that we talk about, this voltage EA is not usually the voltage that appears at the terminal of the generators. Okay. So this EA, right, is still the EA that is internal to the generator. We have not connect the load to the generator yet. So when we connect the load to the generator, there's another type of voltage drop. That's what we call the terminal voltage. The only time that the internal voltage is the same as the output voltage, we call it V phase over here. Okay? Is when there's no armature current flowing. In other words, yeah, if I can draw the circuit out, you have your stator, and you have your poles, yeah, your windings, okay, and then you got your rotor over here. Okay, so when we generate voltage, yeah, the EA, okay, think about it this way, your EA, right, will stay on the surface of the winding over here. Okay, the winding will come out. Okay, the EA will stay there. Okay, this is still a generator standalone that has not been connected to the grid. So the moment we connect to the grid, we have a particular load. Okay, we have a particular load. Then you have a voltage drop. This is the voltage we call the terminal voltage, given by us with this symbol. Okay, and then this is the voltage at this point. It's what we call the EA. All right, given to us by this EA. Okay, so what this green color words is saying that if there's no load, then this V phase and EA will be the same, of course, right? Because if let's say if I can redraw the circuit, it will be like this. Okay. So if I measure the voltage drop over here, when I measure the voltage drop over here, the voltage drop over here will be equal to the current multiplied with the load over here. If there's no load, then the voltage here will be same as here, right? So this is what it's saying. The only time when your EA, right, is the same as your V terminal is when there's no load at the armature side, okay? So this is what we have known, right? So this is just to strengthen what we have known so far. So when the generator rotor is spun, voltage EA is induced in the stator windings. But a three-phase stator current flow will produce a magnetic field of its own in the machine. So we now turn our rotor, okay? So rotor induced voltage at the stator, okay? Then the stator now has current flowing, and the current flow on the stator will produce magnetic field of its own, okay? So now initially we have only a rotor magnetic field. The rotor magnetic field induced current in the stator. Stator now got magnetic field, so we got two magnetic field now. And this stator magnetic field and the rotor magnetic field will start to interact, okay? Or in other words, the stator magnetic field will distort, okay, the magnetic field of the rotor, okay? So stator magnetic field distort the original rotor magnetic field, changing the resulting phase voltage. So this effect is what we call the armature reaction, okay? Because the stator current affects the magnetic field which produced the stator current in the first place. Okay, so we have a way to counter armature reaction. Okay, we normally deploy damper windings, okay, to counter this armature reaction. Why this armature reaction is dangerous? Yeah, we look at this. It's dangerous because we initially expect that what we have in this magnetic field will produce the EA. In the ideal case, this EA is what we expect it to be produced, and then we get a V terminal at the output. But actually it's not like this. Actually, right, the stator current flow will have magnetic field of its own, affect this rotor magnetic field, weaken the rotor magnetic field, and eventually weaken our induced voltage. So this is a back and forth process. Okay, it's constantly like 2 steps forward, 1 step back kind of relationship between the rotor and the stator magnetic field. Okay. Okay, so now we want to examine. We're going to derive some mathematics. Yeah? Now we're going to go through some mathematics. We want to derive some useful equation. Okay, so we will go through the trouble of deriving the equation so that we will come down with a very nice simple equation that we can refer to manipulate our synchronous generator. Okay, so that you know how we can operate our synchronous generator. Before we go into the mathematics, right? So I just want to explain this diagram first. We will go back and forth, right? We'll go forward and then we'll come back to this diagram, back and forth, so that before I go forward, I will explain the diagram first. Okay. So these 4 diagrams, they are the same, but they are in different state at different time, right? A, B, C, D. So this is when the rotor magnetic field is in line, right? Is in line with your EA, okay, the EA. So from now onwards, I will just refer to EA. EA refers to the induced MMF. Yeah? It's not the terminal voltage. And then in the state B here, you have a lagging. Okay, the resulting voltage produce lagging current flow when connected to a lagging load. Okay, so you connect to a load. So typically our load is a lagging load. So when you have a lagging load, okay, you will have a lagging current. So the lagging current, if you can plot the phasor diagram, this is a phasor diagram, where the current will lag the voltage. Okay, this current will lag the voltage here. So this is what is happening in this phase, in this state, like this diagram B. In the diagram C here, okay, it shows that the stator current, okay, now the stator current, which is the IA, produce the magnetic field of its own. This is what we call the stator magnetic field. We call it the DS. Okay, which produce, okay, its own stator magnetic stator voltage. We call it E stat. Okay, so not to be confused with these many numbers of parameters here. Yeah? And this BS, okay, and the BR, the stator magnetic field and the rotor magnetic field, they will produce a net magnetic field like this one. Okay, somewhere in between the BR and the BS. Okay, the net magnetic field, which is related to your terminal voltage. All right. Okay, so far so good. Okay. All right. So just to add on, yeah, the BR, the BNet, yeah, the BNet is the interaction. Okay, as a result of interactions between your rotor magnetic field and the stator magnetic field, then you get the net magnetic field like this. So the drawing here, right, is not necessarily like this. It's just to show the random process, okay, the random locations of the BNet, but we draw it somewhere here, okay. And your terminal, okay, your terminal voltage is due to your induced voltage EA and also the stator voltage. All right. So now we want to derive some equation here. Okay. So notice that, right, the E stat, right, the E stat lies at an angle 90 degrees behind the plane of maximum current IA, and the E stat is directly proportional to current IA. So notice in fact this diagram. This E stator, yeah, the voltage of the stator, if you're looking at the diagram D in your slide, yeah, the E stator is at 90 degrees behind the Imax. Okay, 90 degrees behind the Imax. So if that is the case, yeah, I can express, okay, I can express my relationship of E stator and also the IA, which is the armature current, with this relationship, negative J XIA. Okay, the negative there is due to the lagging. Okay, it's due to the lagging, okay, of the stator behind the IA. So if I have this, okay, then I know that this is the voltage drop. Okay, the voltage drop due to the load. Okay, so if I redraw the circuit, so you have your EA, IA, is your X, okay, your inductor. So normally we use inductor to represent our load because most of our load are lagging load. So lagging loads, they have only inductance component, okay. So your EA, yeah, so the circuit goes like this. Okay, the circuit goes like this. EA, this this we call the voltage drop V theta. So EA minus V theta is the voltage drop along here, which is IAX. Okay, that's how you get it. Okay, so rearrange the equations. Minus IAX V theta. Okay, so that's how we get this equation. Alright, and because of this is an imaginary, we put a J in. So this is how this equation is obtained. Okay, so if we can draw the diagram for this equation, yeah, it is like this. Okay, you got your component of IA, drop along the inductor load or the lagging load, the voltage EA minus this, okay, this voltage minus this voltage, you get this voltage. So this is what this equation is saying about. Yeah. Okay, so this is the first relationship that we have, that we can derive for our synchronous generator. So remember, yeah, this one is your terminal voltage. This is your MMF, your induced voltage, right? So this is the voltage you get at your load. This is the voltage supplied by the generator, and this is the inductance, okay? The drop, okay, the drop. So there is a difference here. The generator that you produce, and also the voltage that you receive at the end of the load, okay? So that is the first relationship. Okay, then there are more to it. The stator, okay, the coil of the stator, okay, the coil of the stator, which is, let's say I have a diagram there. Okay, if you look at this diagram, yeah, this stator, yeah, they have coil, okay, that's wrapped around the poles over here. Okay, the windings, the stator windings themselves, yeah, they have resistance and they also have reactance. So those can cause voltage drop as well. So we need to, what we have over here, this is the ideal case. The non-ideal situation, we need to deduct more things. So we deduct the voltage drop across my stator reactance and the voltage drop across my stator resistance. So this X and this R, right, is given to me by the stator windings. Okay, so together they are called the synchronous reactance. So I think this one normally is provided by the manufacturer, synchronous reactance, right? We call it XS. XS. Yeah. So we can simplify this as EA minus the XS minus the RA. So that will be my terminal voltage produced by a synchronous generator. Alright? Okay, so that's good, yeah? Okay, so let me write this down. Your V theta EA synchronous armature. Alright. So now we have this we are still in the equivalent circuit of a synchronous generator, right? So let's try to take a look at this diagram over here, yeah, on the right hand side over here. Remember that we are trying to produce a three-phase voltage, okay, three-phase output voltage. So under the situation where the three-phase voltage is balanced, yeah, we can analyze the voltage on a per phase analysis, meaning that phase A, phase B, and phase C, they are the same. Okay, and I can represent them as an individual circuit of their own. Okay, but they are just phase shifted by each other by 120 degrees. So this is what a balance and a per phase analysis is about. Yeah. So I have a rotor that is rotating. I have a rotor that is rotating inside my generator. It will induce voltage in the stated three-phase winding: first phase, second phase, and third phase. Okay, and this is what we have obtained. Okay, earlier on we know that the synchronous generator at the stator side, right, is given to us by this equation, and this equation, right, represents that you have EA, XS, RA. So this is what is represented by this equation. Okay. And this is what we get in each of the phase, which is drawn by this tree diagram over here. Okay, the phase 1, phase 2, and the phase 3. Yeah. So this is your rotor. Remember, your coil, your rotor, you have a DC source. Okay, DC source that we apply at the rotor side, and then, of course, in your rotor you also got your resistor and so inductor, and you got what we call this field current. Okay, field current. So in actual case here, we want to be able to control what is our field current, because right, initially when the generator starts to rotate, the field current will be very large. There's a huge inrush of field current. So what we do is that we insert an adjustable resistor here. So initially we put a large value to this adjustable resistor so that this is low, so that we don't burn our field, our windings. And then as the generator starts to rotate faster and faster, then only we reduce this resistor value. So this is just a way for us to control the total resistance in the windings to protect our circuit. Okay. Okay. Earlier today,